Okay, so that is basically by solving this minimization problem mathematically. So how do we solve that minimization problem mathematically? Now we have to use the concept of a basis we just introduced a little bit earlier. Because f has to be restricted in this x, saying that minimization over all f within this x is the same as saying minimization over, in the last example, a1 and a2, right? So for f0 minus a1 times, I think let's say that b is a basis that is equal to let me use h1 and h2, right? So b is my basis. So for any f can be represented as a1 times h1 plus a2 times h2, right? So saying that minimization over f is the same as saying minimization over a1 and a2. So what I get is f0 minus a1 times h1 minus a2 times h2, f0 minus a1 h1, a2 h2, right? Okay, so then the problem has been reduced from a very non-intuitive functional analysis problem, right? This is functional analysis, minimization over a class of functions, right? Which is kind of tricky, into a very simple problem, just a minimization over two numbers, right? And then even better, this can be this is equivalent to minimization over a1, a2, and we use all of these properties of an inner product. We know that the inner product can be expanded just as if it is a product, right? So by expanding it, we have, okay, f0, this is one term, and let's do it maybe a little bit slowly. So yeah. So I won't actually do all the math over here, but you can imagine minus a1 times h1 and f0 plus etc. Right? So there are linear terms, there are quadratic terms. The quadratic terms would have a2 minus a1, a2 times a1 and a2 times a2, etc. Right? There will be linear terms and quadratic terms. So what I'm saying is that if we can compute all of these inner products, then the minimization problem becomes a minimization over a quadratic function, which I believe we should all know how to solve, right? Minimizing a quadratic function is basically equivalent of solving a linear problem, because basically the derivative of this objective function with respect to every single, with respect to a1 and with respect to a2 has to be 0. All right, so basically all of this has been reduced into a linear system. If we have the basis, if we have the function, and if we can compute these inner products, which for this case is just the integral between these functions. All right, so that's where the idea of finite element comes from. Yes?
How do you get quadratic term?
Oh, this is because I have this term in a product with this term, right? For example, so this becomes minus a2 h2 minus a2 h2 when you expand it, right? And then you use this property, right? So you pull a1 out, you pull a2 out. So minus h2 minus a2 h2, and then you use this property, so you exchange it. And then you use this property again, so you get minus a2 square minus, well, this is plus, and then h2, right? So yeah, you pull it one at a time. All right. Yeah.
Can you explain again the meaning of the basis function? In this case, h1, h2, how does it relate to the previous plot potential?
Right. so h1 and h2 is h1 and h2 are functions that goes from 1 to 0 and from 0 to 1. So going to here, it's a function, h1 is a function that goes from here to here. h2 is a function that goes from here to here, right? And you can imagine by doing linear combinations of these functions, you can get to this function. Yeah. And solving this minimization problem is just figuring out what is a1, what is a2, that gives me that closest function to whatever I draw. Okay, so this is the idea of finite element. And if we, instead of approximating a function, if we want to solve a differential equation, we do the same thing. We suppose the solution, we approximate the solution to the differential equation using, again, the linear combinations of such, using linear combinations of these basis functions. And then we plug this linear combination into whatever differential equation we want to solve. Okay? And then I have, in general, I have a residual, right? The residual cannot always be 0 because I have restricted my space into a pretty restrictive set of functions. Okay, but like instead of forcing my residual to be R0, we want to force the approximation of the function with finite element to be 0. We want to force the approximation of the residual using this type of approximation to 0. Then we solved this equation. And again, so we have seen that it is pretty difficult to draw some function that makes the finite element thinks it is 0. So if our residual approximated using finite element is actually R0, then the residual should be, we hope, pretty small. So that's how finite element works. All right. Yes?
So using these linear basis functions, what order of accuracy is that?
Depending on functions, depending on the differential equation. For example, if you solve Poisson's equation or heat equation or linear advection equation, all of these equations, if you approximate it using piecewise linear, you get second order accuracy. So we are going to discuss that. So the analyzing the order of accuracy with finite element is a little bit more tricky than finite difference, but we will discuss this later. All right. Yes?
I was just wondering for that quadratic problem if you ever have to worry about like multiple solutions.
If you want to set the quadratic function to 0, you have to. But minimizing a quadratic function, you shouldn't worry about it, right? As long as we can prove that the quadratic function is positive definite, then you shouldn't worry about multiple solutions, right? Because you should have a unique minimum. We are not looking for solutions to a quadratic problem. We are looking for the minimum of a quadratic problem. All right, which is actually the solution to a linear problem. Okay, so let's discuss a little bit in more general projection. So this is a very specific example, right? And we can see like working out the math is a little bit tedious. So let's figure out, is there a way to simplify in a more general sense to something a lot simpler before we put it into a discrete math?